Hello, I'll be giving a brief tour of the CPU that I've built in Minecraft. That is the main program memory block, holds 16-bit words. This is where they're input. You can write at location 0 and then choose to write at the next location. They are not edge-triggered D flip-flops, so whichever location it's writing to, if you change one, it changes immediately. And this has problems sometimes that if I go to write at the next location, it will erase the next location and put in whatever is represented there. This is a downside to my CPU. It basically means it's very difficult to edit one line of code. If you want to change the code, you have to write the entire thing again. This is the random number generator switch. This activates the random number generator in my ALU. It's on a separate switch so that by the time you've walked over there to flick the on switch, it will have essentially become random, using the time it takes you to walk between the two switches as a random factor. Display control, that just resets all the values on the display to 0. This is the clock. It's a 24 clock. That's about 4.8 seconds per period, I believe. All the mossy cobblestone are edge-triggered D flip-flops. There's 8 of them to every column, and each one can be activated and set to one of these two output buses or input buses to the ALU. From there, it comes into the ALU. Most of the ALU is the adder, subtractor. This is it here. For anyone who's familiar with what redstone adders and subtractors look like, you'll notice that this one is very, very large. That's because I designed it. It's custom built to be fast. It takes two 2-bit numbers at a time, and using a sum of products method, it calculates both the outputs, whether it's carry or no carry. So once it's got all those outputs from every single input, it then has a selector at the other end near the bus that runs through very quickly and selects which output will be set to the bus on the other side that gets sent back into a register. It takes only one torch change, one torch delay, to produce 2 output bits. So once the first carry is known, the rest of them can be calculated very, very quickly. I think in 0.4 seconds after the first one is known, the rest are known. So if this was ever to be expanded to 16-bit, it would only require an extra 0.4 seconds to get the result, which I'm very proud of. It took me the most amount of time and was the most annoying part to build in the CPU. I've actually got a prototype of it where I was testing it on the other side of the encoders and decoders for the screen there. In case you're wondering how the random number generator worked, it's basically a series of clocks that cycle outputs. They're all based on prime numbers, so there's no really obvious pattern to it. And combined with the slow sampling rate of the main clock, it produces apparently random numbers, which is random enough for anything that my CPU can do. These are 4-bit registers that take in 4 bits and send them out to the screens over there, the 4 7-segment displays. And it basically takes 2 of those buses and produces a hexadecimal output. This is a giant, actually I guess it's fairly small. It's the encoders and decoders I built for the screens. They take the 4-bit input there and convert that, well, from there that decodes it into, the top bit decodes it into just like a decimal number, you could say, where there are 16 lines and only one is active. This bottom bit encodes that 1 bit and produces the number however it should look. This is the prototype for the adder. I'll just give you an example. So let's do the equation that uses a lot of carry. All ones, there's the output, that one there. Now if we flick this, that's how quickly it operates, which is fairly quick. So that's about it. Thank you for watching. I hope to have some more videos up later.